Hi, I'm Michelle, and this video is on the AP Calculus BC 2007 problem number 6. The problem states, let f be the function given by f of x, which is equal to e to the negative x squared. There are 4 parts to this problem, part A, B, C, and D. The main concept in this problem is Taylor-Maclaurin series. For this particular problem, it is very important to know the power series representation of e to the x. For future problems like this one, the power series representations of sine of x, cosine of x, tangent of x, and ln of 1 plus x will also need to be memorized. Part A. Write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 0. Since the problem gives us what f is, we can find the general term of f using a power series representation of a function similar to f. Then we can figure out the first 4 non-zero terms based on our general term. The function that is similar to f, which is e to the negative x squared, is e to the x. The power series representation of e to the x is x to the n all over n factorial from n equals 0 to infinity. If we look at the function f, e to the negative x squared, we can observe a similarity. The negative x squared in the function f is equal to the x in e to the x. Therefore, negative x squared can substitute the x in the power series representation of e to the x. We get negative x squared to the n all over n factorial. Simplifying gives us negative 1 to the n, which results from the negative x squared, times x to the 2n, because 2 and n can be multiplied according to exponential rules all over n factorial. This is the general term of the function f. Since the problem asks for the general term of the Taylor series for f about x equals 0, we just leave the x as is. The second part of part A asks for the first 4 non-zero terms of the Taylor series for f about x equals 0. As said before, we can find these 4 terms using the general term that we found in part 1 of part A. So once again, the general term of the Taylor series for f about x equals 0 is negative 1 to the n times x to the 2n all over n factorial. So as defined by our power series, we start from n equals 0 all the way to n equals 3, since we need 4 terms. N equals 0 gives us 1, n equals 1 gives us x squared, n equals 2 gives us x to the 4th power all over 2, and n equals 3, which is our 4th non-zero term in the Taylor series, gives us x to the 6th power all over 6. Part B. Use your answer to Part A to find the limit as x approaches 0 of 1 minus x squared minus f of x all over x to the 4th power. So moving on to Part B of the problem. Part B is only one point, and that point is for the answer. So it doesn't really matter what intermediary steps you take to get your answer. So I'll be showing you the method that I use and what I think is the easiest method to use. So I substituted f of x with the first 4 non-zero terms in Part A. And this many terms is more than enough terms to answer the problem, as you'll see later on as we finish Part B. So we get 1 minus x squared minus, in brackets, 1 minus x squared plus x to the 4th power all over 2 minus x to the 6th power all over 6. And all of this is over x to the 4th power. So we can cancel the 1's since 1 minus 1 is 0, and the x squares since it's negative x squared plus x squared, and we're left with negative x to the 4th power all over 2 plus x to the 6th power all over 6, and all of this is over x to the 4th power. We can break the complex fraction into 2 parts, since the 2 parts of the numerator of the complex fraction have the same denominator. Simplifying these 2 fractions gives us negative 1/2 plus x squared all over 2. Since the limit calls for x approaching 0, the x squared all over 2 is reduced to 0. The final answer of Part B is negative 1/2. Part C. Write the first 4 non-zero terms of the Taylor series for the integral from 0 to x of e to the negative t squared dt about x equals 0. Use the first 2 terms of your answer to estimate the integral from 0 to 1/2 of e to the negative t squared dt. There are 2 ways to do this problem. The first way is slightly longer but more conceptual, whereas the second way is faster and less conceptual. We will start off with the first way. The power series representation of e to the negative t squared is as shown. This is from part A of the problem. We can substitute x in place of the t since we will be taking the integral of this power series with respect to x soon. So when we take the integral of the power series representation of e to the negative t squared with respect with x, we get negative 1 to the n times x to the 2n plus 1, since when we take antiderivatives, we add 1 to the exponent power. Then we divide the numerator by the new exponential power, which is 2n plus 1. Therefore, the denominator is 2n plus 1 times n factorial. As defined by a power series, we start from n equals 0 up to n equals 3, since we need the first 4 non-zero terms. And plugging in n equals 0 all the way to n equals 3 gives us the following terms in green. That is the answer to part 1 of our first method of part C. We will continue to use this method for the second part of the problem. The second part of the problem requires us to evaluate the integral from 0 to 1/2 of e to the negative t squared dt using the first two terms. To do that with the first method, we plug in 1/2 as the x in the antiderivative of the power series representation we found in part 1 of part C. We can simplify by moving 2 to the 2n plus 1 to the bottom, according to exponential rules. Then, to evaluate the integral, we simply plug in n equals 0 and n equals 1 to achieve two terms. The terms are 1/2 and negative 1/24. When adding these two terms together, don't forget to minus the second term, since the second term is negative. We get the final answer of 11/24. Now we will solve part C using the second method, which is faster. First, we will list out the terms of the Taylor series of e to the negative t squared. This is the same as the answer from part A. Then we take the antiderivative of each of these terms with respect to x, since it is the integral from 0 to x of e to the negative t squared. These are the first 4 non-zero terms of the Taylor series for the integral from 0 to x of e to the negative t squared dt about x equals 0. To estimate the integral from 0 to 1/2 of e to the negative t squared using two terms, we simply plug in 1/2 as x into the first two terms we found in part 1 of part C. Adding the resulting values gives us a final answer of 11/24, which is the answer we got using the first method as well. I would recommend using the second method on a test since it is much faster than the first method. Explain why the estimate found in part C differs from the actual value of the integral from 0 to 1/2 of e to the negative t squared dt by less than 1/200. The third term of the integral from 0 to x of e to the negative t squared dt is x to the 5th power all over 10. That, evaluated at 1/2, where we basically plug in 1/2 as x, gives us 1/320. 1/320 is less than 1/200 since 320 is bigger than 200, and thus the estimate found in part C differs from the actual value by less than 1/200. Since the integral from 0 to 1/2 of e to the negative t squared is an alternating series with terms that decrease in absolute value to 0. So essentially the limit as n approaches infinity of this integral is 0.